Math is perceived as one of the most boring subjects in school. Lit allows creativity to flourish, science involves exciting labs, and history even has amazing and true stories that have happened. But math? It's just numbers. Students tend to think, why even learn math? I'm never going to use this in my life. But that mindset is entirely untrue. Math is involved in nearly every aspect of life. You like business? You gotta know math. You like medicine? Gotta know math. You like space? Definitely gonna have to know math. There are some people out there who love science but hate math. And sorry to break it to those people, but math is an enormous part of science, especially space topics and research on planets, solar systems, and our universe in general. Math is an integral part of determining what possible feats are, as well as the entire engineering basis of the topic. So today, we are here to show you how math is involved in space topics like planets in the form of Kepler's 3 laws of planetary motion.
Math, especially calculus, can be applied to nearly every aspect of space as it involves mostly physics-based topics. Gravity, orbit, energy, work, force, etc. are all space and planet-based topics that heavily involve math. First off, a German astronomer and physicist, Johannes Kepler, created 3 laws of planetary motion, all involving the application of derivatives. For example, in Kepler's first law, he states planetary orbits are ellipses with the sun at one focus. Through the derivation of the original position using polar coordinates, we can display the acceleration of different planets along specific areas and radial positions around the sun. For example, we take the original formula for the radial position and polar coordinates of the planet based in space around the sun, and then take the derivative of the equation to find the velocity vector. Once the velocity vector is found, then we can take the second derivative of the first equation, the derivative of the velocity vector, to then find the acceleration vector of the planet, since acceleration is the derivative of velocity. This important calculus topic of derivatives is applied to find significant information in order to prove Kepler's first law of planetary motion. If the polar coordinates, acceleration, and velocity vectors all work for Earth to travel around the sun in ellipses, then his law is proven. It is also used to determine if the orbit of the planets are changing in any way, possibly by an outside force or environmental change. If the orbit is changing, then the velocity and acceleration vectors found through the derivative of the original equation should change accordingly.
Kepler's second law of motion also directly involves the application of calculus. Kepler's second law is, planets do not move with constant speed, but the line segment joining the sun and the planet will sweep out equal area in equal times. To get to the importance of Kepler's second law, however, we must first delve into the equation of Newton's law of gravity, G capital M lowercase m divided by r squared. From Newton's equation, we can input the net force equation of force equals mass times acceleration to find the acceleration of the planet. We had the values of Newton's equations, and when we apply them, the small m cancels out, leaving us with capital G capital M divided by r squared. Through algebra, we can determine that the force equals the opposite of this equation, and we set it equal to AR. Next, we can determine A theta is just equal to 0, since the acceleration is only towards the sun, leaving other angles with no component. Therefore, A theta equals 0. With these values established, we have a system of 2 nonlinear equations that we can use to finally use for Kepler's law. Using the second equation in the system, 2 r derivative, theta derivative, plus theta second derivative equals 0, we can derive Kepler's second law. Once derived into r squared theta derivative equals c, some constant, we can apply it to an integral equation for the area swept by a polar curve. To help with understanding, an integral is essentially an antiderivative meant to be interpreted as an area, swept by the line joining the sun to the planet. Next, input the constant c for the 1 1/2. You should end with the result of c t1 minus t0 equals 2, divided by 2 as the area, thus meaning the area swept only relies on the amount of time. This proves Kepler's correct that the planet sweeps out equal areas in equal times. Now, off to Nick to explain the math behind Kepler's third law.
Thank you, Nick. Kepler's third and final law of planetary motion describes the relationship between the period of orbit of a planet and the semi-major axis of the orbit of the planet. The law states the square of the period of the orbit of a planet is proportional to the cube of the semi-major axis of the orbit. In geometric terms, a semi-major axis is half of the diameter through the longest section of the ellipse, essentially a line coming from the center going towards the furthest away point in the ellipse. In order to derive Kepler's third law, we must first find two formulas for the area of the orbit. The first formula involves the perihelion, the closest distance in the orbit to the Sun, and the aphelion, the farthest distance in the orbit to the Sun. The base formula we will be using for the area is equal to pi times a times b. The first equation for involving the perihelion and the aphelion aspect of the orbit is a equals perihelion plus aphelion all over 2. This will be plugged in as our value in the original area formula. Next, we find b through simple Pythagorean theorem. We know that through symmetry, the distance from the Sun to the ellipse along the hypotenuse will be equal to a, while the other sides are b and another value f. So, through Pythagorean theorem, we find that b is equal to the square root of a squared minus f squared, which then results in b is equal to the square root of the perihelion times the aphelion. Now that we have our two equations, we can plug them in our values of a and b in the original area formula, which ends up being area is equal to pi times perihelion plus aphelion over 2 times the square root of the perihelion times the aphelion. Now that we have our area formula, we need to find the values of the perihelion and the aphelion. Using the formula r is equal to 1 divided by g times n divided by c squared minus a cosine delta, r acts as the distance from the Sun, so we just need to find the minimum of r, the perihelion, and the maximum of r, the aphelion. Through this, the perihelion equals 1 divided by g times m divided by c squared plus a, and the aphelion equals 1 divided by g times m divided by c squared minus a. Now we can plug these values back into the equation we found for a, the semi-major axis, which results in the semi-major axis equaling g times m divided by c squared divided by g times m divided by c squared minus a squared. Now we need to relate this back to the period of orbit to show the proportionality and prove the law. To do so, we plug in the value for our semi-major axis as well as a constant c into the formula. C times t divided by 2 equals a, but with the exponent of the denominator of a to the power of 3/2, so we are able to get the semi-major axis cubed. After some algebraic steps, we end up with the equation of t squared equals 4 pi squared divided by g times m times the semi-major axis cubed. This expression effectively proves Kepler's third law that the period of orbit t squared is indeed proportional to the semi-major axis cubed with a constant of 4 pi squared divided by gm.
As you can see, math is a very important part of our universe. Kepler's laws, while significant, only cover a minuscule portion of one specific subject of space, an infinite realm. Math can be applied to every other aspect of this fascinating area that is just outside of our tiny planet, as well as most on Earth itself. Without math, it would be impossible to logically prove many theorems, ideas, and hunches that led to amazing discoveries. To all those people who hate math but love learning and research, just know that we wouldn't understand nearly any of what we can learn now without the perfect applications of math.